Okay, so welcome everyone. Thanks all for being here. So today it's our great pleasure to have Konstantin Matetski, so from Colombia, who will be telling us about directed mean curvature flow in noisy environment.
Thank you very much for the introduction. Thanks to everyone for showing up here. So I'm going to talk about my joint work with A.Gerasimovic and Martin Heyer. So Andres is a postdoc at the University of Bath. And so the work is basically done, but okay, so it will take some time to post it on arXiv because as always, there is a problem with papers about regularity structure that they are very long. So it will take some time to make the paper shorter. All right. So generally speaking, the motivation of our work is the so-called weak KPZ universality conjecture. So proving, okay, so we're not going to prove the conjecture, but basically we're going to show that, as always, the KPZ equation plays a very special role in random growing interfaces. So we will consider a very special model which describes a random interface, and then we prove that this model converges after scaling to the KPZ equation. And another motivation was to analyze a special class of stochastic PDEs, the PDEs which are driven by inhomogeneous noise. So meaning that the noise in the equation depends on the solution to the equation. And so it happened that this equation cannot be put straightforwardly into the theory of regularity structures. And so we wanted to tune the theory so that we can also work with these equations. And so the outline of my talk will be the following. So before talking about the main model, I want to spend some time talking about the quenched KPZ equation, which is an interesting model in the KPZ universality class, and very little is known about this model. So then I will talk about our main model, the mean curvature flow on the plane, and we'll state the main result. And then I'll try to explain you what are the main difficulty with this equation and how we can put it into the framework of regularity structures. So basically, there are two problems which I'm going to talk about: how to make this equation locally subcritical and how to deal with inhomogeneous noises in the framework of regularity structures. Okay, so let's start with the quenched KPZ equation. So what it is written here. So it has all the terms as the usual KPZ equation in one dimension. The nonlinearity is given by the derivative of the solution squared. The only difference is that the noise is inhomogeneous. So what it means that usually the equation is driven by space-time white noise or modified space-time white noise, depending on time and space variable. So in our case, we replace the time variable by the solution to the equation. Okay, so to do this, we of course need to consider the noise to be smooth. So we consider modified space-time white noise. But of course, when the noise gets rougher and rougher, then it becomes difficult to make sense of the noise without saying of making sense of the whole equation. And so this model is very natural if you think about random growing interfaces. So the KPZ equation is the model which describes such interfaces, like, for example, burning paper. So I always try to provide a picture here. So there is a random growing interface. And so you think that, so the upper part of the picture is a sheet of paper, which is burning. And then there is a fire front, which is propagating up. So then the random perturbation of this fire front comes from inhomogeneity of the paper. And what it depends on is where the fire front is located. So it depends on the height of this phi front and at the spatial location, which is exactly the inhomogeneous noise which we have in our Quenched KPZ equation. Okay, so so we add some extra constant force at the right-hand side, and depending on the value of this force, there are several conjectures about the behavior of the Quenched KPZ equation. So more precisely, one expects to see the so-called pinning-depinning transition, depending whether f is large or small. So if you consider f large, then the force on the right-hand side will dominate the noise. So the solution is expected to have a linear trend in time. And so roughly speaking, the inhomogeneity in the noise behaves as the usual noise where the solution u is replaced by the time variable. Okay, so roughly speaking, in this case, the equation looks like the KPZ equation. And so one should expect to see the KPZ fluctuations of the solution. So in other words, if we apply the KPZ 1 to 3 rescaling, so rescaling of the vertical fluctuations t to 1/3, the correlations t to 2/3, then when t goes to infinity, and the solution should converge to the KPZ fixed point. So on the other hand, if the force is small, then the solution wants to stay pinned. So what it means is the following. If on some interval the solution stays constant, then there is no contribution, there is no random perturbation coming from the noise. Okay, and so eventually one expects that the solution u completely stays fixed. And so there should be some critical force which describes the phase transition between these two regimes. And so as I said, there is not so much known about these conjectures and about this equation. So there are plenty of physical papers which do some simulations and do some maybe not very rigorous computations.
Okay, can I ask a question?
Yes.
Hi, Konstantin. It's Jean-Christophe. You mentioned the comparison with the burning paper.
Yes.
But do you expect this pinning phenomenon to occur in this context?
No, because you have a constant speed to go up.
So when does pinning occur?
So the pinning occurs when f is small. So if you take f to be 0, then you should expect that the solution stays fixed.
But when burning paper, f cannot be small. That's what you mean?
So in the burning paper, there is always a constant speed to burn up. There is always a linear trend to go up.
Okay, I see. Got it.
You're subtracting a renormalization in addition to f, right?
Well, yeah. So there is another question: how to make sense of the nonlinearity? You need to renormalize it, but this is a different story.
But like you sort of saying f is you've already made it mean 0 without, if f is 0, then the thing has mean 0.
Can you say it again?
If f is 0, then f is 0 corresponds to being mean 0 solution.
Right.
Is that what f being 0 means? Because that's like
right,
not
okay,
actually true.
Thanks.
Yeah, I guess that's right.
All right, thanks. Sorry for the interruption.
That's all right. Yeah, so there are plenty of physical papers about this equation, but I couldn't find any rigorous mathematical result. So what we want to do, we want to take this model in the KPZ universality class and to tune it such that we get the KPZ equation instead of the KPZ fixed point. And so there are two natural ways how to get the KPZ equation from a random growing interface. Either we introduce weak asymmetry, we multiply the asymmetry by some small parameter squared of epsilon, or we multiply the noise by some small parameter, which is called the intermediate disorder regime. Okay, so we need to have the constant, the force to be constant, and for simplicity, we take it to be 1. And so in both of these regimes, the rescaling of the height function is slightly different. So in the first case, it is multiplied by square root of epsilon, while the space-time rescaling is parabolic. So in the second case, we don't have this multiplication. But okay, at least heuristically, in both cases, we can see that in the limit, we should get the KPZ equation. So we want to work with the second regime simply because it is a particular case of our more general model which we consider. But although we could also prove convergence in the first case. Okay, so let's see heuristically why we should get the KPZ equation. So if you look in the intermediate disorder regime and rescale the function in this form, then the rescaled equation is given by this. Okay, so we see the structure of the KPZ equation. So the renormalization constant, which we need to subtract, appears in the nonlinearity, and if everything goes well, as in the usual KPZ equation, we expect to have a non-trivial limit of the nonlinearity. And the renormalization constant is typically of order epsilon to the -1. So then the noise, the rescaled noise is approximating the space-time white noise. When epsilon goes to 0, we get convergence of space-time white noise. And the inhomogeneity in the noise is expected to behave well. So if C epsilon is of order epsilon -1, then epsilon squared times C epsilon should vanish in the limit. And if H epsilon is approximately the solution to the KPZ equation, so it is a Hölder continuous function. So when we multiply a Hölder continuous function, we should also expect it to vanish in the limit. Okay, so when epsilon goes to 0, then we really see that we should get the KPZ equation. And what is important in this rescaling, that we also subtract epsilon -2t term, and this is the one which removes the constant force at the right-hand side. Okay, and so after subtracting this term, it appears as t in the noise. So if there was no force, we would get there would be no t, and then so we don't get what we want in the limit. So our result is the following. So we can choose a renormalization constant such that if the rescaled initial conditions to the Quenched KPZ equation converge to a Hölder continuous function with Hölder regularity greater than 1/3, then indeed we have convergence of the rescaled solution to the Hopf solution of the KPZ equation in the respective topology. So in our case, it's locally uniform topology and in probability. Okay, so the heuristics looks quite simple, but the proof is not trivial. And there is an obvious problem with this equation that when you work with the KPZ equation, you always want to apply the Kohl-Hopf transform to simplify it to the stochastic heat equation. In this case, it doesn't seem to work, because even if you apply the Hopf-Kohl transform, the noise stays inhomogeneous, and you have to work somehow with this inhomogeneous noise. And so it would be interesting to try if we can prove this convergence in some simpler way. Okay, so in our case, we use regularity structures, which allows us to do it. Okay, so now I will call about a more general model, which we were initially interested in, the mean curvature flow on the plane in 2 dimensions. So the model is the following. So we have a function in the plane, the function of the x variable, and we look at its evolution as a mean curvature flow. So in other words, at each point in the plane, the speed of the function, so the normal speed of the function is given by this expression. Okay, so we have the kappa, which is the mean curvature of the function at this point. We have some constant term. We take it for simplicity to be 1, and this is the term which plays the same role as the constant force in the Quenched KPZ equation. And we take the weak random perturbation. So we have square root of epsilon multiplied by some smooth noise. Okay, so we have a random mean curvature flow in the plane. And so if we start with a function of the variable x, so we expect to stay at any time as a function of the variable x. So if the geometry or starting plane a role, so we don't have a function of the variable x, we have some loops or whatever, then our analysis would not work. Okay, but in our case, at each time point, we have a function of the variable x. And so it is not difficult to derive a PDE which describes the evolution of these functions. So the evolution is given by this random PDE, where the randomness comes from the normal speed v, which is as before curvature plus 1 plus square root of epsilon eta. Okay, and the curvature can be computed explicitly, which involves the first and second derivative of the solution. Okay, so we want to analyze the scaling behavior of this random PDE. And the precise result is the following. So first of all, we consider the epsilon periodic case simply because it is much easier to work in a compact domain than on the whole plane. And we consider quite regular initial conditions of the flow. So we need to consider the initial condition to be Hölder 7/3, where we allow the derivatives to blow up when epsilon goes to 0, but this blow up happens with the given rates. So we need to control how fast they blow up. But what is important is that the initial conditions after rescaling converge to the Hölder continuous function with a Hölder regularity 1/3. So again, after that, we can choose the appropriate renormalization constant so that the rescaled mean curvature flow and properly renormalized converges to the solution of the KPZ equation. Okay, it is not very clear what is like the optimal choice of the regularity of the initial condition, but so because of the method which we are using, we need to take it to be quite regular. Hölder 7/3. All right, so now I will try to provide some heuristics. Again, why do we even expect to see the KPZ equation in the limit? And if we write the equation for the rescaled process, the stochastic PDE looks like this. Okay, there is some nonlinearity on the right-hand side, which looks quite complicated. It involves first and second derivative of the solution. And the noise is non-homogeneous. Again, inside the noise, we have the solution, but again, this solution is multiplied by epsilon squared. Okay, so if H epsilon behaves as the solution to the KPZ equation, again, we expect the non-homogeneity to disappear in the limit. So analysis of the nonlinearities is slightly more complicated, but heuristically it goes like this. So again, the derivative of the solution squared in the KPZ equation explodes as epsilon -1. So if you multiply it by epsilon squared, so it should vanish in the limit when epsilon goes to 0. So in particular, the first nonlinearity on the right-hand side is expected to vanish when epsilon goes to 0. Also, the multiplier of the noise should give us 1. So this term will vanish. We will have square root of 1. And this term is exactly an approximation of the derivative of the square root. So when epsilon goes to 0, it approximately behaves as 1/2 of the derivative of the solution squared. And then if we choose a renormalization constant appropriately, then this is exactly the renormalization which appears, it's exactly the renormalized nonlinearity which appears in the KPZ equation. Again, at least heuristically, we can see the structure of the KPZ equation in the limit. But so analysis of this equation is quite involved. So because of the two reasons. So first of all, the nonlinearity is quite complicated. And second, the noise is non-homogeneous. Even though we expect it to vanish in the limit, for every fixed epsilon is there. And then if you renormalize, like for example, this product in the equation, so you usually you renormalize by the expectation of the noise convolved with some kernels of the noise squared, and then this term, the non-homogeneity from the noise, appears in this renormalization constant. Okay, so the analysis of the whole equation is quite non-trivial, and so now, after the theory of regularity structures have been introduced in 2013, I guess, there was a huge progress to make kind of a black box result. So given an equation which satisfies certain properties driven by certain noise, the black box result should give you like almost automatically convergence of this equation to the one of the equations, like for example, the KPZ equation. And okay, so I will. Okay, so this is the Martens picture to describe how the regularity structures work. Basically, we feed to the black box 3 objects: the initial condition of the SPD, the noise, and the function f, which describes the nonlinearity. And then, so in the theory of regularity structures, we leave this object to some more, some bigger space, and we prove convergence in this bigger space, which is called the space of model distributions. And then from this bigger space, we reconstruct back the solution, the solution of our SPD. So, and if the convergence holds in terms of regularity structures, then the convergence holds also in terms of the classical solutions. And so, as I said, now this framework works almost automatically. So due to the 4 works by Martin Heirer and his collaborators, so the theory of regularity structures was done by Martin Heirer, then by Brune, Heirer, and Zambotti, they developed a general renormalization mechanism, which tells you if you have a nonlinearity in the SPD, how it should be renormalized. So in the result by Brune, Chandra, Cheverev, and Heirer, they showed how this renormalization acts on the actual equation. So if we renormalize equation in terms of regularity structures, how the actual equation changes. And then in the result by Chandra and Heirer, they basically proved convergence. Okay, so they prove convergence on the level of regularity structures. Okay, so we have this general result, and so we want to feed our equation to this black box to get automatic convergence, but the problem is that in fact our equation is more complicated than those which were considered in the framework, and I want to explain you so why we cannot apply the theory directly to our equation. So there are 2 main problems with our equation. First of all, the noise is inhomogeneous. So in all these problems which were considered before, the noise was just the usual space-time or spatial noise, but it wasn't dependent on the solution to the equation. The second is that our equation is not locally subcritical. And what it means, I'm going to tell you in a minute. Okay, so I will start with a easier problem, how to make our equation locally subcritical. And I will start with saying what does, roughly speaking, means to be locally subcritical. So we can consider a more general equation, stochastic PDE, driven by inhomogeneous noise, which depends on the solution to the equation in the way which was before. And on the right-hand side, the nonlinearity is given by some function f, which depends on epsilon derivative of solution times second derivative. Then another function f2 depends on epsilon derivative of the solution times the derivative of the solution squared. Okay, so we can prove convergence of this more general equation to the KPZ equation, and everything what we need to assume is that these functions. Oh yeah, and then the noise is also multiplied by some function f3, which depends again on epsilon derivative of the solution. So everything what we need to assume is that all these functions f1, f2, f3 are sufficiently regular, and we need in our analysis C6, and some values and derivative of these functions should vanish. Okay, so if we take the simple choice f1 is equal to 0, f2 and f3 are equal to 1, then this equation immediately turns to the rescaled quenched KPZ equation. And then if we make the choice of the functions more complicated, as you see in this equation, then our general equation turns to the mean curvature flow. Okay, so there is no need to make one of these particular choices. We can work in the generality. And the problem with this equation is that the nonlinearity which appears on the right-hand side is too irregular. So what does it mean? So the space-time white noise is a Bessel distribution with regularity smaller than -3/2. Any value alpha smaller than -3/2. So then the Schauder estimate suggests that the solution to this equation in the best case, has a regularity of the noise +2. And then if we take two derivatives, then the regularity of the second derivative of h is again C alpha. So in other words, this term has the same regularity as the noise on the right-hand side. And okay, so roughly speaking, this means that the equation is not locally subcritical. So to have a locally subcritical equation, the noise should be the most irregular term on the right-hand side. So and it happened that in this case we can turn this equation into a locally subcritical one, but it needs some effort. It needs introducing some extra equations, and the trick is the following: if we expand the functions f1 and f2 into the Taylor expansions, then what we see is that these powers of the derivatives of the solutions are always multiplied by some positive power of epsilon. So in f1 we have epsilon to the n in each term, and in the Taylor expansion of f2 we also have epsilon to the n in each term. And the trick is to use this multiplication by epsilon as an improvement of regularity. So what does it mean is the following. Okay, so let's see, we have the nth term in this Taylor expansion. Okay, so assume that, okay, we can make sense of this product. Then the best what we can expect is that this is a best of it's a distribution, the best of space of the regularity alpha -1, which is the regularity of the derivative of h times n. This is the power here, and plus alpha. And alpha is the regularity of the second derivative of h. Okay, so as soon as we stay on the epsilon scale, as soon as we work with the modified noise, for each fixed epsilon, actually h epsilon is a smooth function. So what this really means is that for each fixed epsilon, this product should diverge as epsilon to this power. And only when epsilon goes to 0, we should get really a distribution, an actual distribution in this space. So in other words, this power tells us what is the power of epsilon at which this product diverges. So if you multiply this product by epsilon, the rate of divergence in terms of epsilon should be improved. Okay, so in other words, we can use epsilon to the n to improve this regularity by n. Okay, and now if we compute all these regularities, then in fact the nth term, each term in the stellar expansion has a better regularity than the space-time white noise on the right-hand side. And the same trick can be played with the function f2. Again, we use epsilon to improve the regularity. So when n is equal to 0, so there is no power of epsilon, and we have the KPZ type regularity, derivative of h squared. But as soon as n is greater than 1, greater or equal than 1, we have a positive power of epsilon, and we improve the regularity. And again, so this allows to write the equation as a locally subcritical one. For this, we need to use all the powers of epsilon in some efficient way, so that we use all of them to improve regularity as much as we can. And it happened that to use all of them efficiently, we need to rewrite our equation as a system of equations. So more precisely, we do the following. We take the solution h epsilon to our equation.
Sorry, Konstantin. In the previous slide, so in the Taylor expansion of f1, why n is at least 2?
Oh, because okay, so we made some assumption. Okay, so the first derivative vanishes, and the zero derivative can be taken into the linear part.
But then in your formal argument, right? So you mentioned a formal argument. If you just formally send epsilon to 0, then you get a Laplacian. Oh, a Laplacian on the left-hand side. Sorry, I didn't see that. Okay.
The Laplacian is here.
Yeah. Sorry. Yeah.
Okay, so what we do is the following. So we take our equation h epsilon to the rescaled this general equation, and we introduce some auxiliary functions. So hi are defined as h times epsilon to the power 2i over 3. And then respectively, we need to define the noises and the renormalization constants. Okay, so we need to have 4 of such functions, and then we write the equation for each of these functions. But now, okay, so if you write the equation accurately, okay, so on the right-hand side, the new functions, the linearity, non-linearities are described by new functions f1, f2, f3. Okay, so I provide them here. Okay, so these are quite nice functions. They have good behavior. But what is important is the following. In the equation for hi, we use a second derivative of hi plus 1. And the hi plus 1 has a better regularity. Okay, then the i's equation is driven by 3 noises, psi I plus 1, psi I plus 2. And the last equation for h3 is, okay, given in this form. So so it is driven by the third noise psi 3, and we take the second derivative of h3, but it happened that the third equation can be solved classically. So it is a quasi-linear equation. We have a second derivative of h here, second derivative of h here. We can solve it classically, and we can use a theory of regularity structures to solve the first three equations in this system. Okay, so we made our equation more complicated, but now we have a system of locally subcritical equations. So now the theory of regularity structures can be applied. And okay, so just to see why it is locally subcritical, we can again perform the same heuristics as before. So the noise psi I is expected to have regularity alpha, the regularity of the spacetime white noise plus 2i/3, and this is the power of epsilon by which we multiply the noise. Okay, and then okay, so psi I appears in the equation for hi. So again, the Schauder estimate tells us that the solution to the i's equation should have the regularity of the noise plus 2. And then if we take the second derivative of hi, again, we have the same regularity as the noise, but now in the i's equation, we use the second derivative of hi plus 1. Okay, so what we get is that this term has better regularity than the driving noise, and we're in the good shape. And then, as I said, there is no problem with the last equation because it can be solved classically. Okay, so another difficulty with this equation, as I said, comes from the non-homogeneous noise. So the noise is dependent on the solution, and it doesn't fit into the theory of regularity structures. Okay, so I will try to give you at least a slight idea about how we deal with it, but okay, so it's quite difficult to do it without going into the details of regularity structures, but okay, I will try my best. Okay, so let's look for simplicity at the quenched KPZ, rescaled quenched KPZ equation. Okay, so what does the theory of regularity structures do? So it allows to raise the solution H to some more abstract space. In other words, we consider some element capital H of a space of model distribution, which is given by an expansion in some basis. Okay, you should always think that you have an expansion. You should have a Taylor expansion in which you replace the monomials by some other objects. Okay, so in particular, in the Taylor expansion, we have the constant term, which is given by the solution H, and we have some higher order terms. Like in the usual Taylor expansion, it would contain the derivatives of H. But okay, so in the regularity structures, they contain some more complicated objects, but which also include the derivatives of the solution. And then the reconstruction map, R epsilon, tells you how to go from the abstract space to the space of functions and distributions. So if we apply the reconstruction map to this model distribution capital H and evaluate it at the point Z, we recover the classical solution to our quenched KPZ equation. So what we do now is the following. We view the driving inhomogeneous noise as a function of this abstract solution, abstract model distribution capital H. And we write a Taylor expansion of this function around this point. So formally, it looks like this. So we introduce some symbol which depicts the noise psi epsilon. This symbol will be just, okay, this node. And we define this inhomogeneous noise on the abstract space as a function of the model distribution. So what we do is we Taylor expand the inhomogeneous noise around this point H. Okay, so formally it will look like this. So we have the usual like sum in the Taylor expansion 1 over n factorial. So this red term tells you how many derivatives of the noise you should take and at which point you should evaluate you should evaluate the noise after taking the derivative. Okay, so in other words, we have a couple of two objects. On the right-hand side, we have our node, which depicts the noise. On the left-hand side, we have a delta function, the derivative of the delta function. So the order of the derivative of the delta function n tells us how many derivatives of the noise in the time variable we should take. And the centralization point of the delta function h of z tells us that, okay, after we computed these derivatives, we should evaluate the derivative of the noise at this point hz. So as soon as we have some regularity of the solution to the Quenched KPZ equation, so that the model distribution belongs to one of the spaces of model distributions, we can show that this map is a map from one space of model distributions to another one. So it takes this abstract kind of Taylor expansion H, and it gives us another Taylor expansion just with a different order, because okay, now we have some extra term, some noise, which multiplies the elements, and so the order of the elements will change. But okay, so we have a nice map on the level of regularity structures, and now we want to define a way how to go from this map to the inhomogeneous noise in our equation. So what we do is the following. We take this reconstruction map and postulate how it acts on the symbols which appear in this Taylor expansion, on these red symbols. Okay, so more generally, instead of the delta function, we can take any distribution in some appropriate space of distributions. I call it B. And then we define the action of the reconstruction map on this pair, the distribution and the element which depicts the noise. Okay, so by definition, we say, okay, this is equal to the integral of our smooth noise with respect to this distribution, which is here. Okay, so why is it a good definition? Because if instead of mu, we plug in this delta function, then this convolution will give us exactly the nth order derivative of the driving noise in the time variable evaluated at this point hz. Okay, and now okay, so if we define everything appropriately, and if we apply the reconstruction operator to this map psi of h, on the right hand side, what we obtain is simply the Taylor expansion of this driving noise. Okay, so which gives us again the driving noise which we want to work with. Okay, so basically it tells us the following. The building blocks in the regularity structures, in the regularity structure in which we work, should be of this form. We have some abstract symbol which depicts one of the elements in the equation. It can be the noise, it can be the noise convolved with the heat kernel, and so on. And we take a pair with some distribution. And this distribution tells us at which point the noise is evaluated and how many derivatives we should take. Okay, so we have a collection of these basis elements, and in fact, it creates a little difficulty because so the set of these basis elements is infinite because mu is in a set of distributions. Okay, so there is a way around of it, because usually in the regularity structures you want to have a finite dimensional space. But okay, this is not. There is a way how to deal with it. And after that, using these basic elements, we recursively build elements of the regularity structure. So how do we do it? we do it in the following way. So if you want to, so P is the heat kernel, and if you want to describe the heat kernel convolved with the noise, we just depict it by this tree. So the node is the noise, the edge depicts the heat kernel. And again, as soon as we have one noise in this tree, it should be paired with a distribution mu, which tells you so how to treat this noise, how to evaluate the noise, and how many derivatives to take. So if we take the derivative on the heat kernel convolved with the noise, so we can okay, we introduce a new h, a dashed h, which corresponds to the derivative of the heat kernel. And then if we multiply the two derivatives, then roughly speaking, what we need to do, we need to multiply two elements of the regularity structures. Each element is a pair, distribution and a tree, distribution and tree. And it will give us another tree, which simply multiplication of these two. We just attach the roots of these two trees to get a double cherry. And again, so in the tree, we have two noises. So it means that we need to have two distributions, which corresponds to each noise. So what we do is we need to take this mu1 and mu2 and attach this pair to this tree so that we should know which distribution corresponds to which noise in the tree. Okay, so using this idea, we can build recursively the basis in the regularity structure and then solve our equation using the, in this basis. And so what I want to say that to analyze the equation, the mean curvature equation, which we want to analyze, we really need this general machinery developed by all these guys, because so the basis in the, so although the equation looks not so complicated, the basis in the regularity structure is very complicated. So the number of trees which we need to analyze is 72. So there is no way to analyze each tree by hand. So we need to exploit like this big machinery so that it can prove convergence of the equation for us almost automatically. Okay, and I will stop at this point.
Thanks. So are there questions for Konstantin?
The 72 elements, most of them have epsilons.
Right. So those who don't have epsilons are those which are in the usual KPZ equation, I guess.
2 or 3 or something.
Yeah, maybe 4 of them, I don't remember.
Yeah, 4 maybe, yeah. Okay.
Yeah, and the others have epsilon. And then, yeah.
Do you have an invariant measure for this stochastic mean field, mean curvature flow?
Okay, this I don't know. We didn't even ask this question. No, I don't. No, I don't know.
So the deterministic mean curvature flow is a gradient flow. It's L2 gradient flow for the length of the curve, I think.
Right.
Because it's essentially the curve shortening flow, right? In one dimension. But actually in any dimension, in high dimension, if you have a like m-dimensional manifold embedded into Rn, then the mean curvature flow is also the L2 gradient flow for the volume. It's a general fact. So I don't know, well, the kind of noise you add into the equation is maybe some sort of stochastic quantization or something, but I don't know.
I don't even know what is the effect of this strange noise.
Right.
Question, I don't know.
Are there other questions?
I have a question. So the quenched KPZ equation, you have this noise that depends on the solution, which you're kind of arguing because the solution has this drift, it's going to look like it's going to sort of end up looking like it's decorrelated in time. But I guess there's going to be some sort of microscopic coloring in time. And I was just wondering if you color the noise in time in sort of a more conventional way, is there an analogy you can draw between those systems at kind of the level of the regularity structures or at the microscopic level somehow?
Can you say it again? I didn't get it.
So at the microscopic level, you kind of expect there to be some sort of coloring in time because the solution will actually sort of go up and down and
Right.
sort of feel the same noise sort of multiple times.
Mhm.
But there's sort of more conventional ways of coloring the noise in time also. And so I was just wondering if there's a way using the regularity structures to draw some kind of analogy between those, like is the C epsilon kind of related?
Okay, so what is a more conventional?
We'll just take the noise and just mollify it in time, so the equation feels some kind of time correlated noise.
Oh yeah, this is what we always do. So psi epsilon, you should think that this is a modification, space-time modification of the white noise.
Okay,
Yeah. So this
but
is
can
what-
you relate it to the KPZ equation, like the regular KPZ equation, with the mollified noise also?
Right. This is yes. Yeah.
Okay.
Yeah. Yeah. So for each epsilon, you have a colored noise, but then when epsilon goes to 0, this coloring vanishes. Yeah. So you really get the KPZ equation from an equation like this with colored noise.
So Konstantin, if you do this scaling where you get the usual KPZ equation, even though the noise is somehow quenched, do you know how you would get something different than that? Can you actually make sense of the quenched KPZ equation as a scaling limit if you don't do that, or is there something trivial or?
Okay, so it depends what you mean. Like as soon as you have a smooth noise, then there is no problem to make sense of the quenched KPZ equation. But then, like of course, if you plug in space-time white noise here, then like I have no idea how to. Well, it doesn't make sense. Like of course, to evaluate the space-time white noise as the solution.
Yeah, well, that's what I mean. Okay.
But it's just like you expect kind of additional coloring coming, even if you could interpret it for space-time white noise, there'd be sort of additional coloring coming from the fact that the noise is depending on the solution.
So it really depends on the strength of the force on the right hand side. Like so as soon as we keep this force constant, then this gives us like this T term in the noise.
Okay, so it disappears in the limit. Nice.
Yeah,
But
yes.
like, I guess, Alex, is what you're saying somehow that if you have a very weak force, so that you're kind of moving through the noise field, but in the time scale of the scaling limit, that it's almost as if you kind of create a temporal color.
Yeah, I feel like they should correspond to sort of an additional coloring of the noise. They would.
So there maybe there's some intermediate forcing scale where you actually get a scaling limit, which is a colored noise.
Yeah, or maybe like a better convergence rate if you adjusted the color of the other one to sort of account for the additional coloring.
Yeah, that's a good question. But yeah, so we did not try to see it.
But if you go back to the next slide, can you just manually remove those counter terms? The big constant, I mean, physically they should be there, but it's still a valid question if we redefine the noise by removing those counter terms. And I think that will correspond to what Ivan asked.
So okay, then you need to control the difference of the inhomogeneous and homogeneous, right? So you mean if we remove this inhomogeneous?
No, the first two.
Oh, the first one.
The first two actually.
Oh, the first two. Okay, no.
Or just the first one. I mean, so that what remains is a convergent, what's supposedly a convergent process.
Yeah, that's a good question. Yeah, so my answer is I didn't try, but maybe, yeah, maybe it was trying. I cannot say no.
Are there other questions? Okay, let's thank Konstantin again and for the great talk.